Sometimes the biggest picture, it's actually painted with the most meticulous details. And today, well, that's exactly what we're diving into. We're taking a really deep look at these incredible multi-dimensional maps of our own Milky Way galaxy, specifically the ones from ESA's Gaia mission, Data Release 3. So our mission today is to unpack the profound insights these maps offer us, revealing the structure, the dynamics, chemical composition, even the history of our galaxy. We want to find those surprising nuggets of knowledge that help you become truly well-informed about, well, our cosmic neighborhood.
And it's really important to grasp that these aren't just, pretty pictures. What's truly remarkable is that they are powerful projections, multidimensional. They use our galaxy's own coordinate system. Think of it like the Milky Way's own GPS. Each map tells a distinct, really critical part of our galaxy's story. And this builds on the first anniversary of the 34-month Data Release 3, which was June 13th, 2023. This deep dive, it's really a testament to collaborative science, a huge global effort behind these visualizations.
Okay, let's unpack these astonishing maps then, piece by piece, see what they show us. First up, something that honestly blew my mind. Star motions. We're looking at a map showing predicted star displacement 400,000 years into the future. How do we even predict that? It's like Gaia's looking into a cosmic crystal ball.
Well, it's less crystal ball, more incredibly precise science. What's fascinating here is that these predicted trails, they're not just theory. They're based on Gaia's extremely accurate measurements, current positions, current velocities. The insight this gives us is a glimpse into long-term dynamics, stability, or maybe surprising instability of, say, star clusters. It helps us figure out if parts of the galaxy will stick together for ages or, just slowly drift apart.
That's a wild thought. Okay, so from the future, let's jump back in time. Next map. Star ages. This one's based on what? A random selection of 10 million stars from DR3. Blue for the youngest, red for the oldest stars. And what really jumps out is where those old red stars are mostly found.
Exactly. This map uses data crunched by a specific part of Gaia's software, the Flame module. Think of it as Gaia's specialist tool for calculating stellar ages and other properties accurately. And the big takeaway, most of the oldest stars are outside the main galactic disk, in the halo. It's not just a vague clue, it strongly suggests these old-timers are like cosmic fossils, relics from a much earlier time, maybe a more chaotic formation era. Before the spiral disk we know really formed, they tell us about the Milky Way's baby pictures, especially.
Really puts galactic history into perspective. Okay, now let's talk about how we actually see these stars, or rather, how things get in the way. This next map shows star brightness, and it specifically highlights the effect of extinction, is that right? Caused by interstellar dust, so it's like looking through a kind of cosmic fog.
That's a perfect analogy, yeah. This map uses a specific color measure, G-degree GRVS. It's derived from the radial velocity spectrometer data. Basically, it's Gaia's way of measuring how a star's light is changed by its motion, its composition. And after it's been affected by all that dust, understanding how this dust dims and reddens starlight is absolutely critical, crucial. Without correcting for this, our cosmic measurements, our rulers, would be way off, and our whole idea of the galaxy's 3D structure would be flawed, seriously flawed.
Okay, so measuring that cosmic fog is key for accurate maps.
Yeah.
Got it. Speaking of key measurements, panel 4, variable stars. Specifically, 134,000 RR Lyrae stars. People call these cosmic yardsticks. What's so special about them? And what are these maps showing about their metallicity, their iron content, FeH?
Great question. RR Lyrae stars are fantastic yardsticks. They pulsate, right, in a very predictable way. And critically, they all have roughly the same intrinsic brightness. So if we know how bright they really are and how bright they look to us,
We can calculate the distance.
exactly, calculate their distance very precisely, lets us map huge areas of the galaxy, and by analyzing their light curves the way their brightness changes, using Fourier analysis, we can figure out their chemistry, like their iron content, FeH. Now, what's really fascinating here is that these yardsticks, they also work as chemical tracers. We see higher metallicity, more iron in RR Lyrae stars in the Milky Way's central bulge compared to those out in the halo. That difference points to distinct populations, different origins, maybe different formation histories. And look at the Magellanic Clouds. Fewer RR Lyrae stars in the small cloud compared to the large cloud. That hints at different evolutionary paths, different chemical enrichment histories for these neighbor galaxies as they interact with our own. Each star's chemical fingerprint tells a story.
That's incredible, like galactic genealogy. Okay, Building on that dust idea, panel 5 gives us a more detailed look, the extinction map. This one shows extinction for individual stars based on 470 million sources. That's
Yeah.
just a huge number.
It really is immense. And what this map does, especially when you connect it back to the brightness map we just talked about, is it gives us a much more direct, more granular view of exactly where that obscuring dust is located. It's essential for, well, peeling back those dusty layers to see what's truly behind them. It helps us refine our 3D model of the galaxy with just unprecedented precision.
Okay, now here's where it gets really interesting for me. Panel 6, interstellar medium. This shows the distribution of diffuse interstellar bands, DIBs. Color code by equivalent width. What are DIBs? And why is it significant that they're concentrated towards the galactic plane? This is mapping the actual stuff between the stars.
Yeah.
That feels fundamental.
It is absolutely fundamental. DIBs are like faint fingerprints, cosmic fingerprints, left by complex organic molecules drifting in the space between stars. We measure their equivalent width, basically how dark and wide that fingerprint is, to gauge how much of these molecules are there. And there's strong concentration towards the galactic plane. That's hugely significant because that's where most of the gas and dust hangs out, where new stars are forming, where the conditions are right for these complex molecules to actually form. It tells us about the chemical richness of our galaxy's star-forming nurseries.
Wow. So we're mapping the building blocks for planets almost. Amazing. Now a quick but vital piece. Radial velocities. Panel 7. This map shows the Gaia DR3 radial velocities. What's the key takeaway here? How things are moving towards or away from us?
Yeah, essentially. This data is a crucial piece for understanding the full 3D motion. You combine the towards or away motion with the proper motions we saw earlier, the sideways movement across the sky, and that gives you the complete picture, a star's true trajectory through space. It lets us map the galaxy's complex dance in all 3 dimensions.
Okay, full 3D motion. Got it. And what about what the stars themselves are made of? Next up, chemical composition. Panel 8. Colors here show stellar metallicity, MH, which in astronomy means everything except hydrogen and helium, right? Redder stars are richer in these metals, and this is from the GSP spec database in DR3.
Precisely. And this map, it's like a history book of our galaxy, written in chemistry. What's fascinating is that metallicity acts like a literal chemical fingerprint. It tells you about a star's birth environment, its age. Stars formed really early on, in the galaxy's infancy, almost pure hydrogen and helium, but over billions of years, massive stars lived, died, exploded, forging heavier elements, are metals. They enriched the interstellar gas clouds, so redder, metal-rich stars tell us they were born later from that enriched gas. If you connect this to the bigger picture, you can trace the chemical enrichment history of the entire galaxy, from the very first stars right up to today. It's like mapping the Milky Way's own industrial revolution.
That's a fantastic way to put it. Okay, bringing it all together now. Our second to last map, panel 9, space motions. Here, the colors show line-of-sight velocity blue approaching, red receding, and the lines show proper motions.
This is the synthesis. It reveals the intricate, really majestic dance of stars in 3 dimensions across the galaxy.
Yeah.
It's absolutely essential for understanding the overall dynamics, the gravitational pulls within the Milky Way. You see how stars interact, how they tug on each other, how whole streams of stars move together. It paints this comprehensive picture of our galactic home as a dynamic living system.
And finally, panel 10, the big picture. Sky map of brightness and color. This is the grand overview. Total brightness and color of more than 1.8 billion stars from Gaia EDR3. It's just breathtaking to look at.
It really is stunning, and it raises that important question. Just think about the sheer scale of the data here. Over 1.8 billion stars visualized. It's a breathtaking census of our stellar neighborhood. It gives us this unprecedented, singular view of our home galaxy. It's like having a cosmic microscope and a telescope all rolled into one, revealing the true breadth and beauty of the Milky Way.
So as we've walked through these 10 maps, from those incredible future star motions to the chemical fingerprints, they collectively give us just profound insights into our galaxy's structure, its dynamics, its chemistry, its history. It really is a multidimensional portrait of home, painted with unbelievable detail.
Absolutely. And remember, this deep dive into stars within our Milky Way, it's just one facet of Gaia's impact. The mission is also giving us this vast amount of information on objects much closer in our own solar system, like asteroids, and much farther away, too. Beyond our galaxy, looking at distant galaxies and quasars, it really shows the incredible breadth of Gaia's contribution, connecting the very near to the incredibly distant and ancient.
It's undeniable. Gaia's deep dive into the Milky Way isn't just adding knowledge, it's fundamentally revolutionizing how we understand our galactic home. And these detailed, multi-dimensional maps, they really are a shortcut for you, the listener, to get well-informed, giving you those aha moments about the cosmic forces and the long evolution shaping everything around us, revealing things we never thought we could know.
Indeed. And while we focused mainly on the stars in our galaxy today, remember Gaia is looking outwards too. It's mapping solar system objects, other galaxies, quasars across the universe. So, given the sheer volume and precision of all this data, what more do you think we might uncover about the universe far beyond our own Milky Way as Gaia keeps watching and releasing even more data? The possibilities, well, they feel pretty limitless right now.